Yeah, you have to do it outside of our course lecture and do it right up the same thing. Yeah. Like, that's my last.
Whenever you're ready, just go ahead and start.
Yes, sir.
Introduce yourself and what you're talking about.
Yeah, it is ready.
It's okay, so let's go grab some chairs because it looks like we're only registered, but we have lots of people here, so I'll just give you
Take
a
it
chair.
more than more than possible. So it's going to build up. Have you taken this one previously? They may have set him up so that he does more lectures or more write-ups and gets more credit. It could be that, but when I was here for that first week and really the way Professor you described it with that inch. Like it's a set amount, like even for me, if I'm getting one credit here, I have to be here for that for you. Yeah. I don't know. Maybe that's the number. Doesn't matter. Whether I get one for me. Yeah, can't go. Are you using? I got your personal test. Like, what are you gonna do next? It's RFPs for. No, I know, but what, like mine states 20, but it's a secure communication. Oh, I'd have to look it up.
Okay, everyone. Thank you for coming. So before we start, I wanted to share some. Extra. Because we have some extra.
Like an active conference.
Let's start, everyone. So good afternoon. So today we'll be discussing about the practical machine learning applications and how AI sees the world and predict the world and try to find out the real-time scenarios where we can estimate that how AI, we are feeling so much confident on AI or not. Okay. Our main target is like once we are working on AI, machine learning, deep learning, we always see that we are juggling with some prediction accuracies. Okay. And trying to find out, okay, how accurate the model is. And also we try to think about, okay, with that data set, how good the model is performing or not. So, but our target is today is not to find out the accuracies. Our target is today is like how confident we are on that model or how confident on our AI agent where we can trust that AI agent to do our operations. Okay. Now, many AI systems, generally, they were looking for, we just told you that prediction accuracy was the preliminary goal for any AI agents or AI model that we have to generally incorporate in our research. But our main target was not that prediction accuracy. So our main target was like how reliable it is, how robust it is, and how interpretability concept we can include it. Now the safety critical AI must answer the following: like what did the model use as evidence? How stable is that under noise, occlusions, and small object? And where does it fall and why? Okay. Our today's lens for our discussion was like to find out the robust deployment over best case demonstration. The best case demonstration means you have a good data set, you have a one single particular model, and you thought of, okay, this is performing well, and you are shouting, okay, this model is best in the world. But it is not the true in all the cases. We are trying to break it down today. Now, how AI sees the world is like, sees means the computer vision issues. Computer vision or AI sees the world in a different way. They try to interpret, they try to analyze every single pixels, every single moment. The biggest problem or biggest things that we can think about that for our AI, that we can give the input as a data input or real-time input, then we can pre-process the data and augment it. Then also we can go for feature extractions. Then we can have some specific tasks to do. Like we will tell the AI agent or AI model to do certain kind of task. Okay, and after that, we will go for predictions. Here is an example of where we try to predict whether it is a dog or cat. We have a model in between, which will work as a black box. We have no control in between, but at the same time, it will tell you like what is your, it will give you the predictions whether it is a dog or a cat. Okay. Now, the two common computer vision problem or seeing problem is the small object perspection. Then if it is a small object, suppose think about it, if it is a UAV and or even if fighter plane, but taking the picture from the ground is very hard to and then there is a lot of noise involved, there will be a lot of clouds, there will be a lot of illuminations error coming, and that impact the entire images. And after that, once you take the picture of that UAV, the biggest problem will be you may not be able to see the UAV properly because the pixels might be 2 by 2 pixels. Like if it is a resolution of 125 by 125, but still you'll see that only 2 by 2 pixels the UAV is taking. Even if you are trying to enlarge it, crop it, and then finding out how, and then still you will never get the accurate and good picture of that UAV. Also, there is something called distribution shifts. Like generally, for like right now, the current models who everyone is telling is a very good model of AI. Generally, they are always working in the data set, which is kind of ideal data set environments. Like people standing in the closed room where there is no sound, there is no air, wind, there is no pollutions, and the illumination is very correct. People took the picture of their faces and then try to give the model, okay, now identify me. And it will identify because there is no noise involved. The biggest things that we are trying to impose in our AI model is like distribution shift, like try to give some weather, noise, illuminations change, and let's see how the model is performing. Okay, now the dual task AI intelligence, I wanted to show you because there are a lot of research happened, but one of the research, this is like very preliminary research we did. It is like aerial monitoring. Aerial monitoring, we used a dual task AI intelligence. One is what it is, to find out what it is, what is the object is, and then second one is there any risk on it? So first one was we implemented object class classifications whether we'll find out airplane, helicopter, UAV, or drone. The second thing is like we try to find out whether what kind of threat level that there is involved. Low, medium, high. Like if it is a bird, aerial object can be a bird also. So there is no threat. Aerial object can be a commercial plane. There is no threat. Aerial object can be a fighter jet. It can be a threat. Aerial object can be a drone which is delivering Amazon's drop-off. That cannot be a threat. But also aerial object has some bombs included. That can be a threat. You can see some of the pictures has some kind of motions I tried to include for your vision purpose. Like it can be a drop-off of drones. It can be a threat. It can have automatic gun, and then someone is controlling from outside, from remotely. Okay. Now the single backbone of this area is like we tried to implement two outputs. We try to get the two outputs from the single AI model. Okay. Now, one is we introduce efficient B4, which contains global average pool and then concatenations layers, and also there is two fully connected layers. This model is responsible to do two different kind of activities. One is object detections first, like which categories of the object it can fall under, whether it is airplane, helicopters, drone, UAV, or bird. And also there is something called threat level detections. That same model we implemented on the same dataset, which is already available, which is called AVD datasets, Aerial Vehicle Object Dataset, which is publicly available. But the biggest problem of the dataset was, you can see the picture of that images. It is very blurry, very small, and is very hard to detect. Apart from these two corners, which I superimposed it, try to make it a little bit live so that you can feel what is the threat is involved. Now, with that, keeping in mind the biggest problem of the dataset, we have created, like me and Professor Jaman has been created, one specific dataset, which is called AO-DTA dataset, on which we did it during the summertime, and we published it in the IEEE. Apart from that, paper publications, that is a minimal effort that we did, but only thing mostly we did is we published a new dataset. Now, if you take the picture of this QR code, you will find the dataset in IEEE data book. And you may notice that we uploaded the data recently, like last week, and the footprints we got, 26,000 download happened. And once, like 200 people already viewed the dataset, and which I think is a good success for us, for our Southern University. But also, you may notice in our table 3, which I took from the paper, you may notice that the low, medium, and high, the precision, recall, and F1 score or support is very low or very minimum. The value is very minimum in the low and medium range, because the data set which was publicly available before, which has a very small resolutions and very small pictures, we could not take the proper information from it. So that's what, for low, medium threat, it was failing. So what is the problem of that dataset? The problem of the dataset was the clarity, which was missing. So we addressed that clarity in this AO-DTA dataset, which is Aerial Object Threat Analysis. And it is getting very popular. So for your future research, if you wanted to do, please use this dataset for your reference. And it is a very good dataset. Again, with the training curve, it always tell you the deployability story. You can see the curves meets early, which can tell you it's the first convergence is happening. Also, stabilization loss is also happening during the learning is because it is learning is happening in between. Because I can show you this area where it touches the curves, first convergence, and again still the learning is happening. Similarly for this one. Now, we also still need that robustness check because we implemented one model. We implemented two data sets. We introduced two data sets to the model. And now we are thinking about this model is doing perfect. But now we have to think about it, whether it is a robust or it has some kind of failure scenarios. With that, we identified the confusion matrices where you can see the failure rate is there still under helicopter cases and the drone. Some of the cases we have some failure rates. The failure rates because of the, you can see the drones is having failure cases because of the image resolutions again. Even if we try to introduce a new data set, but we are still not fully successful. So that means there's a room to do some more work to make it successful. Okay. Now the threat level, we already discussed. For high threat level, we have a very strong precision and recall, but for low and medium, it's collapse under imbalance or the quality of the image input. Again, we cannot blame the model alone, or we cannot blame the image or data set alone, or the data input alone. So everything altogether can be successful, everything altogether can be failure. So we have to go for optimal decisions where we can get a robust model so that it can give you the sustainable outcomes. So now, from the airspace to the road, a valid questions can be possible that what is the robustness of AI model if we are switching gear from the airspace to road. Now, the biggest thing is like real-time decisions can do the three things. One is timely, it can signal timely, it can prioritize and then some task, and then also their behavior under noise can be good. But now we will try to explore vehicle-to-vehicle communications and try to find out the message priority via graph neural networks. So the questions, the problem statement that we solved here is, once we are in the road, we know that we have a GPS. And if it is a live, like if it is connected online, it can give you that, okay, there is a police ahead, 10 minutes ahead. There is a road accident is happening, is there 10 minutes ahead. So be careful. But okay. But now we are trying to impose a vehicle-to-vehicle communications. We are not trusting only the GPS. We are trusting a wireless communications between two cars or adjacent cars or 10 to 15 cars nearby you, which is within 200 to 300 meters range. And trying to find out, even if it is not visible to you, it may be possible that sometimes suddenly a deer crossing your car. Then your car can signal rest of the other car which is back from you that, okay, please be careful. There is a live deer crossing the course, the roads. So now to address that issues, we implemented real-time vehicle-to-vehicle alerts, which is beyond the line of sight. Here we implemented graph neural networks, which is abbreviated from its GNNs. And then we try to we simulate dataset because the dataset was not available. We simulated the dataset. Okay, and then we try to implement the dataset with some conceptual parameters like vehicles, position, speed, events, priority. And we also give some vehicles positions randomly with 0 to 100 in the road and try to find out the communications in between and try to find out prioritize the informations, like what can be the message priority, because there can be several message can communicate between two cards or several cards, but which message will be having some more priority. So that one we did it using the low, medium, and high priority messages. Okay. Again, the paper got published, but still there are a lot of work to do, and our student is doing the next level of research. So now, our next standpoint will be our decision support. Like we are trying to predict the decisions, but how AI model or AI agent can give us to make a robust decisions. We try to go for prioritizations, not automations. Now, the AI models or AI agent can do three things: escalate critical alerts, reduce overload, and improve response time. That is true. But for the practical next steps, we'll try to integrate our real data sets, which is very much known to everyone, but also we are going to introduce, and which is a new set of protocols, and try to introduce some big noise, like so much noise so that the cameras cannot see it properly, because that way we can simulate the real-time scenarios. So for that, we introduce traffic sign recognitions under noise. And the dataset name is United States traffic signal dataset, which consists of 75,000 images of the data simulated from the DMV data, like our United States DMV data. Once we are going for the driver license test, they're asking for the questions, what is the signals all about? So that is the only DMV data. It was our benchmark data. And from there, we implemented a severe noise on that data. So that in road time, in the real-time road scenarios, once you're trying to introduce your autonomous car to run, now the stop signal may not look red. Stop signal may look gray. Even if it will look like hexagonal, but it will not look like red, because if it is a night time, you may not see red. You may see gray color stop sign. And if it is a foggy, the stop might be looking like you have to make a decision within 100 meters or maybe less than 50 meters, because you may not see that stop sign early. Maybe your camera, like autonomous vehicles camera, cannot see or identify that stop signs early. So that real-time scenarios we introduced, implementing several Gaussian noises. The Gaussian noises we implemented with the factors of 25, 50, 75, 100. Like, we are increasing the noise too much. Also, we introduce Poisson noises and trying to find out how can we create a realistic data where we can introduce that data to the autonomous vehicle for training purpose, so that the autonomous vehicle can give a better, robust predictions. The goal of this project is to resilient perceptions in non-ideal conditions, because we are trying to break the ideal conditions. So we are trying to give the very hard time to the AI model, implementing noisy data, USTS 75K dataset. So if I have to zoom in, you may notice this area, like we have created the dataset, but at the same time, we try to introduce noise levels. The noise levels can be distributed under set 6, like set 1 to set 6. And within that set 6, you can see that even if we implemented our ResNet model, our training accuracies for the real time, like just like DMV dataset, will look like 100% accuracies. Test accuracies is 91.58. But we are trying to, even if after augmentations and several cropping. After that, we implemented our Gaussian noise, which is of STD, standard deviations of 25. And then we got test accuracies. You can see that it reduces 76%. Now, are you able to see that? I'm so sorry. So now for the Gaussian noise standard deviations, we implemented 50%. And then our test accuracies is still, you can see that it is reducing 71.87%. Even if training accuracies that we are always shouting that our model is performing very well, we are only talking about the training accuracies because it is always fictitious. It is giving you wrong information most of the cases, because the real time, once you try to implement AI model, that why it is failing all that most of the cases, because of that. Because we are only giving the ideal scenarios, standalone positions, and then once we will integrate it into the systems, then it is started failing. And then we blame ourselves. It is not like that we should blame ourselves, we should test it properly. So now, next one, we implemented standard deviations of 75, and you can see that test accuracy is getting reduced, 61.53%. And 100 standard deviations with a Gaussian noise, it is 43.99% of your test accuracies. That means if you show the stop sign, there's a very less chance or 50% chance it can identify the stop sign. Like a very high, like think about it, the very cold weather and foggy. You cannot see the nearby car. That time, 41.99% accuracies. Now, if you are introducing that or training the model to the autonomous vehicle like Tesla, it will fail for sure. Okay, so then that's what we need to think about, which model you are introducing and which data set you are giving for the training. So now we also publish this data set, USTS 75K datasets IEEE data port. It is now getting high visibility. At the same time, for set 6, we implemented Poisson noise, which is, we are thinking about Gaussian noise takes some kind of features. Now, Poisson noise, maybe it will work with some different categories of features. We introduce Poisson noise. With the Poisson noise, even if the data has so noise in it, but still, suddenly we can see the surge of test accuracies of 91.34%, which is really impressive. I'm not talking about we did good. It is something like that model is now responding back. So again, the QR code of the USTS 75K dataset is here available. You can use that, and in your future research, it is a very good dataset, and I think it is going to be published in Nature. I don't know, maybe, because they already gave the decisions. I don't know when they will give the acceptance letter. It is still pending, but they already gave some kind of heads up. Next one is how AI predicts the future. Now we are switching gear from our aerial object detections to the road safety, and now we are trying to find out different things. It is called, you heard about CT scan, right? Like once you have to go for, not, God bless, no one should go for CT scan. If someone has to go, think about it, a person who needs to go for CT scan, what happens to the CT scan? It generally take the millions of your two-dimensional images from, taking the slice of your body. It's not physically, virtually, taking the slice of your body's image samples and make it a millions of pictures of it. Like if it is a head scan, they will take this from this one to this part, 1 million pictures. They will make a scatter plot of that pictures continuously. And then where there is a problem, doctor will identify from the millions of the picture. Maybe there is a warning sign. Okay, if something wrong in this, just look into it. Maybe that way doctors can identify. Otherwise, the doctor has to deal with millions of pictures. Our target was for this one is to combine that all the millions of picture of that head scan or body scan, lower or upper shoulder area, then make it a 3-dimensional model, and make it a 3-dimensional model and give it to the doctor, and doctor will move their mouse and find out where exactly the problem. So that means that the doctor will never lose a single point of vision if it is a 3D model repair. So for that, we try to implement like our conditions as a training distributions, augmentations, and level definitions, and when assumptions breaks. So now this is because we have a deep tech grants, we already have several VRs instrument. We try to implement virtual reality and trying to think about, once we have the 3D model ready, we'll give the doctor virtual reality instrument so that they can see and they can move it and they can double check what is the problem is all about. Now with that, With that, we found a good results, but the biggest problem, we implemented CPU in the CPU. Okay. But that's what you may notice that once you can see that it is coming, but it is coming like, in a scattered way because it's not smoothed. Okay. But our result, we got the results. It was done by one of the favorite students, Charlie Dorjian, who graduated and got a job already in the Salt Lake. But I tried to get hold on her, but it is she is busy on her job right now. But I'll find some new students to continue on this project. Okay. Next one. Also, one of my promising students currently in my capstone. So she is doing with the Alzheimer's staging because her family has some issues of Alzheimer's. So she is so much passionate to give some solutions to the society. So with that, we are trying to find out Alzheimer from the very beginning, like Alzheimer disease conditions, symptoms, very early. For that similar different scenarios with a medical healthcare domain, still we are implementing the same framework with a convolution layer, pooling layer, again convolution layer, pooling layers, dense layers, softmax layers, and so on. But once you'll be doing it, you can see that there is a combined data set strategy is always we implemented combined sources. Here also we introduce a new data set and which is combined of the different kind of Alzheimer diseases from the different countries. Countries can impact also, like different environment always impact. So we took United States, Saudi Arabia, Australia, Canada, like 4 countries data set, and trying to incorporate a new, trying to give us some kind of combined data set so that people can have more access to that. So this is the way we try to break the AI model in a way that don't fool us as a prediction accuracy of 100%. I'm going to give you the hard time, and then you tell me whether you are performing well or not. So that way, we are continuously doing the research. Again, I wanted to give you some kind of heads up. It's like in 2016-17, there was AI agent, the AI model was there. Then machine learning came. Then deep learning model came. Again, they are working as a black box. Then after that, after the deep learning, there's something called explainable AI came, when we can pitch in inside the model layers and you can fine tune it. Then after that, generative AI came into picture, which works on I worked on it. The generative AI, it works from some kind of augmentation techniques, which is because initially there was no generative AI. Initially, it was something called GPhi, which is called GPhi techniques. That means once you have an imbalanced data set, suppose I have, like, the university have only one of my picture. Now I wanted to train a model in a way that the model can identify me in the crowd. How can it be possible? Then the GPhi model was taking my one image from the Southampton University and try to augment it in a different ways and find out a different variations of me. Whether I'm looking in the side, they are trying to predict. It is that, like, even if they are putting some noise in it. So that way the GPhi model was working before. After that, once the technique was getting adopted through the researchers, they tried to implement into large language model with a text analysis and finding out. That's what generative AI comes into picture. Now, after the generative AI, we are thinking about introducing specific agent to do specific task. Now, after that, it is coming agentic AI. Agentic AI is a different thing. Agentic AI is, it will work like you. Then they can appoint several agents to do your job. So the agentic AI will be like in future, maybe after 20 years, you may not need to do the job. You can purchase agentic AI model and it can do the job for you. This is the future is waiting for us. Like, suppose I'm teaching, I don't know if the agentic AI can teach my job, I don't know. So yeah, so that's That's something scary and also but something very advanced technology is waiting for us. I heard from recent discussion from the Elon Musk. He's scared about. I was so scared because he was telling that agentic AI, you do not need to do a job. Agentic AI can do the job. It is optional for you if you want to do the job. So those are the things is coming. But again, please do not trust your AI model blindly. Give your AI model once you'll be implementing. I'm pretty sure you'll be implementing, and you are already implemented some. Please introduce some noise. Please give your AI model some hard time and see how it is, whether it's a break point. Give it some pain, and then after that, if still it can withstand, then you can trust it. Like the way our parents trust us, the same thing. We need to trust our AI model like that. Okay, so this is my Google Scholar Play page. If you wanted to join our research team, undergraduate research, please look into the published paper and see if it is fitting in your areas of interest. Then please contact me. Let's cheer for. I'm so grateful. I'm a faculty of Southern University. It has a lot of support for faculties and students. I came from different universities. I know how much we are getting from this university, because I should tell we are getting world-class facilities, even if we are very small university. I'm very much grateful to our associate dean, Matthew Roberts, and you, sir, to support and making this session happen. Again, our Southern University, we have a lot of fundings, still limited, but we have still a lot of funding that we can access as a faculty, as a student. Like I access faculty scholarly support funding, Gibson research funding for my students, deep tech grants from our departments, and it is awesome to have some grants available for doing research with students. Also, I'm so much grateful for our departments of computer science and cybersecurity, and I believe we have a world-class faculty group. Also, I believe in our computer science and cybersecurity student who can rule the world very soon. And also our department head, Professor Glenn Sager, Professor Nathan Barker, and Professor Gary Wallace for supporting me to break the barriers. And also our administrative officer, Crystal Reed, for her immense support in everything. Thank you, everyone. Right now, please clap for CQ. So he published aerial vehicles 1 that IEEE sub-publications happened into 2025. He was the second student with Southern University, where I published work in IEEE. I published several others, but with Southern University, he's the second student. I'm so proud of him. If you are registered for the class, you need to come. When speakers start talking, that is cool. So if you don't come to the class,